again, folks. Today we're going to actually be starting with a new chapter. Yeah, I'll show you. This is the official title of the chapter, and if you're so inclined just to separate out the notes, you could fold over a border like this. This is chapter 3, and we're going to be talking about exponential and logarithmic functions to add to the ever increasing pile of functions, right? Anyhow, I'm going to start with section 3.1, but I want to sort of draw you an overview to see where we're at. So here we go. To this point, we have basically established this list, right? You have your 6 toolkit functions, right? Sometimes they refer to them as parent functions in the context of transformations, which are basically just little tweaks that you would apply, put a number here or there, a coefficient or an extra term or a negative sign to affect the drawing, right? So if you wanted, say, for example, to have your function that is a parabola flipped, all right, vertically, you would basically put a negative in front of the first term. Anyhow, there's a nice symmetry here that I wanted to show you. First of all, if we're talking about functions in general, remember, the proper notation would be an italicized F, a parentheses, and then an X, right? But you know that this is the same basically as if you were to replace this with the letter Y, all right? And I'm just going to stick with that because I think it's a little bit more warm, fuzzy, and familiar, okay? Of the 6 toolkit functions, let's start with absolute value. That's really a super easy one. That would be something that looks like this. All right, we have Y equals X, and the X is distinctly tucked in between absolute value lines, right? And you know that as far as a graph is concerned, what that amounts to, right? This is basically the V shape of a graph, right? More commonly, though, they would start you probably with the polynomial functions. Right? It's a little bit more complicated, but you'll see this one slight alteration as we go through it. Things that are, or functions that are polynomial based, right, basically have these features. I'm going to use a letter up in front like this. Our variable X here, and then these key features. There will be an exponent to generalize. I'm going to use the letter N, all right? And the nature of this, which is really what defines something as being polynomial, I prefer to have that out of all things to be red. That is non-negative. So your exponent, whatever it is non-negative, meaning that it could be a positive, and that's usually the case, or theoretically it could be 0, all right? But it's an integer, all right? So if you train yourself to basically stare at or look for, all right, whatever the integer is attached to the variable X, that will decide what type of polynomial function that you're dealing with. There's some subcategories which, if I had a third hand, would be great. I don't want to make this too complicated, but famously, all right, you have these, all right, a situation where the X is no bigger than 1, all right, and that is referred to as linear, right? This produces, that particular black is not going to show up, let's use this one. These produce linear functions, which are basically just literally straight lines. I hope that's not out of frame. It looks like it is slightly. I don't want to mess with my camera too much. Let's see, that's a little bit better, right? Okay. Linear functions are degree 1, so if you notice that there is either nothing written here, somebody has intentionally written the number 1, you could say that this is a linear function, which is of the category polynomial. All right. Similarly, all right, if you had a variable X and the degree is 2, all right, how would you classify that? This is referred to as the square function. Right. And in terms of a drawing, well, if these linear functions are basically lines, right, just like this is a V shape, then square functions make the parabola shape, which is sort of the hybrid U-V shapes. Neither of those two things technically, because it doesn't have flat size. V is absolute value. It's not quite a U either, because it has a vertex point. Right? It's a parabola. So something that basically looks like this. Right? Versus, say, something that looks like this. Ideally, we would have a, well, I should say ideally, but usually when we have a linear function, it's a diagonal line. It can be horizontal if it's constant as well. If you were to up the ante a little bit further, and say that you tweak this to make it degree 3, all right, then what do you have? With a square function for 2 and a cubic for 3. Cubic is, well, there's no fancy phrase like parabola for that. But if you had the picture, you see how they relate to one another. A cubic function more or less looks like a parabola that's kind of doing the staying alive dance, if you will. So it's up on one side and it's down on the other. If you had something like this, a line curved up like this, and then a second line like this, like one hand pointing that way and one hand pointing this way, you might call that the staying alive. Or if you want to have sort of a mean sense of humor, you could say that it's a parabola that had a stroke on one side, right? Which is mean, sorry. But it's a good way to remember something like this, you know. Anyhow, of the rational functions, they are based upon this one little alteration. I'm going to go back to using green. There is some qualification for the constant that is in the front, right? For polynomials, they have to be real, all right? Which means that you couldn't have the square root of a negative as your coefficient. But what's really key here is just changes made to the exponent. When you have a rational function, they are really polynomial based themselves. It's basically a ratio of polys. So if you saw a polynomial function, a sort of division bar, a line, and then a second polynomial function underneath it, it would be more appropriate to call it a rational function, right? Anyhow, what makes this distinct is that you would have a negative integer sitting here. I mean, remember, an integer also is when you have a whole number, basically, but it's a whole number with a sign. So it's either positive or negative, or in theory, it could also be 0. All right, but the more interesting ones would be something other than 0. Right? You may remember that when you have a negative integer, the effect, I'll put it over here very briefly, is to make something that looks like a fraction. So the very most basic type would be this type. If this was just the integer -1, then this would just simply be 1 over x. All right, you could put the 1 here, no one would get mad at you. But it's unnecessary. All right, anyhow, that's the distinction. You either have positives or 0, or you have a negative integer. And the most basic one, example of this, would be the reciprocal function, which I'll write here. When you have an x, and this is a -1. As I mentioned, this is the effect if you have that situation, an x to the negative first. All right. Now, again, they would refer to that as reciprocal. Okay. Reciprocal function is interesting compared to the others because it has graphs that are not really a polynomial. They are a curve, all right? The curves look something like this. They run this way and they run this way, All right. Anyhow, they also have this key feature. I'm going to put a dashed line that runs down it like so, and a dashed line that runs along the x-axis like so. It has asymptotes. Okay. And then lastly, there's the radical functions. All right. I'll keep switching that up. I really do need 3 hands. I'll learn how to write with my left more effectively. I want to make that a little bit more faint. Anyhow, and if you have something like this, that is based upon these features, y, and again I'm just going to throw just a coefficient up in the front. It's really not imperative that it be there. And then the variable in question is usually x, but just to sort of abbreviate, if you have a fraction rather than an integer, right, written as your exponent, right, remember what the effect of that is. Famously, if you had something like this x to the 1/2, notice that the exponent is not a whole number, it's a fraction. Each of those parts, the numerator and the denominator respectively, right, identify the type of radical that you're going to end up with, all right, and what the exponent on the inside would be. There are some alternative ways of writing this even, but the denominator of 2 would qualify this as being a square root, right? And since square root is the OG, all right, of radicals, roots, right? A lot of times they don't bother to put this 2 here. I think it's nice because to me it's better to over-explain something than to under-explain it. But you're more likely to see this. Math people, for better or worse, are efficient. You know, it's a nice way of saying lazy, perhaps. All right, but they don't put unnecessary information. Like, for example, if there is no number written as an exponent, you assume it's 1. All right. When you're trying to translate from rational notation to radical notation, which is what this is, all right, and we're speaking of radicals specifically, you need to know what this fraction is in order to identify what type of radical you have. All right, anyhow, again, to reiterate, notice that one key distinction: positive whole numbers or 0, negative whole numbers for an exponent, or you have an actual fraction. All right, and actual fractions produce radicals like so. The most basic example of a radical is this. When you have, maybe I'll put it like that. I'll put this with a red radical symbol wrapped around it. And you know that this produces basically this, square root. So, the most basic example to remember is the square root function, right? Y equals the square root, right? The sort of graph that you get out of that, for lack of space, I'll put it here, is again something that simulates a parabola, but it's more or less a sideways parabola. So if you had a parabola that is, again, that sort of V shape, all right, oriented like this, opening up like a flower blooming, all right, you could say that a radical function is something that looks like this, right? The only thing is that there's a technicality here. If we're calling these things functions, then they have to fit the criteria of no repeat x's, essentially, right? So they will very often in a textbook delete out the very bottom of this parabola entirely, right? And just stress that the curve goes from the origin out like so, all right? How come? Because it would fail the vertical line test immediately. One of the ways you could test this, if something is a function, particularly graphically, all right? If we had the bottom of this curve, all right, then if you notice the points that were in alignment with one another, they would have the same x value, and that is a no-no when you want to pass the test of being a function or not. Right? So you're more likely to not see the bottom of this, even though calculation would produce those results. All right? Anyhow, these are our 6 toolkit functions that we have discussed to this point. All right? Absolute value, all right? Linear, square, maybe I should do it like that, huh? I'll do that one last. 1, 2, 3, just to match the exponent, right? 4, 5, and 6 squares. Square root, all right? Now, why am I mentioning this old stuff, which is all hack, right? For the sake of comparison, all right? You know where we have been, now you'll see where we're going. I purposely sort of drew this squiggle here because I want to introduce you to the new functions on this side. Thing is, we have to introduce some new terminology at the same time. Not lose my clips. All right. These functions, all right, there's more than 6 certainly, all right, but these are the 6 that are good to know, all right. They are like tools in the toolbox. If you want to draw something, all right, perhaps you'll go with the V-shape, the lines, parabolas, or these sort of derivatives of parabola. All right. Reciprocal being maybe the one thing that is not at all. All right. These are referred to collectively as algebraic functions. All right. And since we have these 6 to work with that are algebraic, now let's just consider what are non-algebraic. There is another phrase for this, which I actually prefer, and I'll put it here. These are referred to as transcendental. Transcendental. Hopefully I'm spelling this correctly. Transcendental. What does that mean? It means that they are above and beyond the conditions of an algebraic function. There's something a little bit more special. All right. Yeah, still be variables, x's, and such like that. And if we're going to use function notation, you could use f of x or y. All right. But they're beyond the conditions that are merely algebraic. So, the 2 that are relevant, all right, and specifically the 2 that pertain to section 3.1, and then section 3.2 is the other portion of today's show here, all right, are these. All right. There is, let me put this in 2 different colors perhaps. Exponential functions. And then this other one, which are called logarithmic functions. Exponential, and there's this type, logarithmic. And the interesting thing about them in comparison to each other is that they are inverses. Which means that we could craft a logarithmic function in theory from an exponential function and backwards. Right? Remember that these are inverses of each other. All right. Now, sticking with the sort of the model here, right? How would you identify something as being exponential? Well, it'll be modified just a wee bit. Right? I'm going to stick with y equals, and I'm going to put a big capital, well, it's a lowercase b, but a large b here, and then show you how we tweak the input variable, right, which is usually x, right? It doesn't have to be. Notice that these x's, all right, are on the more or less normal tier. When you get to rational, then you could end up putting it down here underneath the fraction bar as a denominator instead. That's the effect of this. But you could write it starting out as having a negative exponent, right? Even if it does produce this. In the situation of exponential, the input variable is itself an exponent, right? And that produces unique graphs that you'll see later. Right? Just making that one little tiny little tweak, right? Moving it off the normal level to superscript of some base, which is what the B stands for. Okay. Logarithmic functions, since it is an inverse, they are inverses of exponential functions, would look something like this in theory. There would be a base number, and there would be an x variable, and there would be a y variable, right? But because they are inverses, the input variable in this case would be the exponent. It would be a y as opposed to an x, right? That's really what is going on here when you have a logarithmic function. The input variable would be written in superscript, right? The thing is, it is not written in that style, right? What you're more inclined to see is, pardon me, a logarithmic notation. So you can see the equivalent of this. The equivalent would be using this phrase. You'd see the word log. The base would be written in subscript, so a little bit smaller, font a little bit lower. X would be written in a parentheses if you want to get really fancy. And then y would be off to the side. I'm going to put the y in red here. Okay. Emphasize its importance, right? If you see y in exponential form as the exponent, then in the logarithmic style of writing, it would look like this. It would be equals y, right? You basically rewrite it so that x is the input, right? But you have to distinguish it from the normal situation here. So anyhow, you put a big block around this. Even though this is what it means when you have logarithmic notation, you have an inverse of the normal condition, you're more likely to see it written like so. Okay, and that is equivalent. We're going to, section 3.2 is about this. So if this feels a little alien to you, don't worry. All right, we're going to cover it when we get there. All right. Okay, so that is meant to be a summary. Let's see. If you wanted to add to this, all right, a more specific type of square function, all right, would be to refer to it as being quadratic. When we talk about a function being quadratic, it just means that it fits the criteria of having three terms in descending order, the lead term being degree 2, right? That makes it square, right? But it's something that could be written in general form, quadratic, or a standard form that is vertex form, or in theory completely factored, right, for different reasons. Okay. There are other non-algebraic transcendental functions. They are the trig functions. So I want to kind of save that thought. There are the trig functions also, but we're not talking about that today. Okay, transcendental. Let me erase this and then we'll start with the new stuff. For those of you folks in section MAT-143, there was this diagram that I had given you a while ago, probably like the first or second week week that we worked together. I'm going to bring it up now just because I want you to see sort of an overview of what the graphs look like. All right. I highlighted and put an asterisk because it's a little overkill. What the diagrams, what the graphs rather, would be, what their domains and ranges would be technically for each of these. Incidentally, identity just simply means that you have the most simplest form of a linear function, which is when y is equal to x and nothing else. It's not special, right? And you'd have a perfectly diagonal 45-degree angled line, right? Here is square, the most basic form of quadratic, all right? Here's square root. As I said, it's sort of a sideways parabola, but we erase the bottom to pass the, what's the expression? Cut the mustard, pass the test of being a function by definition. No repeat x's. Here's your reciprocal, all right? Here's cubic, again, sort of a parabola, but it's slouched on one side. And these are the ones that are relevant now, right? Or something like it. This is specifically when the base number happens to be e, right? But you're still going to essentially see this shape when you have exponential functions in general. E bases are a particular type of those, all right? And then there's the natural log, which is what ln stands for. It's sort of backwards, really. I think it might be French, you know, for that reason, like SI units, Standard International, all right? Units for measurement, all right, originates from French. I think this might be an example of that as well. Natural log. Anyhow, this is the basic shape, no matter what type of log, really, also, right? This is just a specific type. This is a specific type of this, all right? And those are the sections, respectively, right? Here's absolute value, all right? 1, 2, 3, 4, 5, 6 are original Toolkit functions, and now we have these. If you want, print this out, and again, do like I had done, you know, asterisk or maybe highlight to go, this is what I should know, as tools, right, to choose from. Right. Let's evaluate. And to that effect, all the special effects. I'm going to pull out my other whiteboard, see if I can fit it behind here, sort of use it for its grid. I had it for another class, but I might be able to repurpose it. Take that away. See my lovely grains of plywood that I have here. Oh, the special effects. Yeah, this is upside down on purpose because I don't want to use those headings. All right. And since this is a little confusing, let me get rid of this now. Hopefully my acrylic will hold up to the pressure and not break. What I could do is rotate this as well. There we go. Alright. I want to evaluate, give an example of evaluating an exponential function. And in order to do that, I'm going to perhaps do the most brute force thing, which is to randomly choose some easy input variable, x's, right, numbers. All right, so -2, -1, 0, 1, and 2 are really easy to use. They're small and they're familiar, and they don't produce too large a result, really, unless the function itself is really, really complicated, and it won't be. Let me evaluate. I'm going to insert a value, all right, into a function, and perform the operation, and it will spit out an output, which will be, in tandem at least, a dot, all right, on a coordinate plane. So let's say that we had this. You know what? While I'm here, let me dig up a ruler, make a straight edge. Let's see. This is probably overkill, all right, but hey, I'll do it anyway. I'd like to produce a straight line if I can help it. I was never really good at that. This is going to get me in trouble. So, take the top off first. Flip that back, it's in the frame, and draw. A straight line if you can help it. It's never going to be right. This is going to be a little bit too much, but it's all right. I just need the grid lines, basically. So let's change the headings here. All right, we're going to build a table, an input-output function table to generate some coordinates, some ordered pairs, some dots, literally. We'll call this x's for the inputs, and I'll write the function here, and we'll do the work. This will spit out a y, and then we'll produce some coordinate pairs. Right. Again, the easiest x's to use would be the smallest. So maybe I'll go one number lower than I usually do. 2, 1. -3, -2, -1, 0, 1, and 2. And you might wonder, well, where did you get those from? I just randomly chose them, and I would encourage you, if you ever have to do something by hand, use small numbers. Like 0 is super easy to use, 1 is really easy to use. And having a nice spread of negatives and positives, right, will flesh out the drawing a little bit better. So here's the function, right, that I want to perform this work on. Y equals, I'm just going to duplicate this. And it's starting to fade out on me too. Base 2. Is that visible? I think it's okay. It's another dud. Thankfully I have lots of blue. Right. And we'll put the x's here. All right. The most basic incarnation of an exponential function would be a number higher than 1. All right. Because if you had 1 there, all right, what would you get? All right. Let's see. You just keep getting 1, right? As far as non-negative integers are concerned, all right. So that's not really going to be too interesting, right? If you have, right, these numbers to insert here, 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 and here, we're going to perform the arithmetic and see what that spits out now, right? So I'll maybe doodle on top of this. If I inserted -3 here, right, what's the effect? The effect, as long as it's legible, if you have a negative to start with, is that you really have this fraction, right? 1 sitting on top of 2 to the third, right? Again, if I insert a -2 here, right, you end up with this fraction, 1 over 2 squared. Right? One more of these. If you stick a -1 here as an exponent, you end up with a fraction 1 over 2 to the first, right? Making them denominators makes essentially the negative go away for all intents and purposes. All right. 0. You would have 1 over 2 to the, no, that's not the point, no negative. It's just 2 to the 0 at that point, right? It doesn't make a reciprocal. This one is 2 to the first, and this would be 2 squared, all right? Now, as far as the arithmetic is concerned, what would you get? Well, remember the instruction of exponents, it's glorified multiplication. Right? So a regular ordinary multiplication is just one number times the second number. When you have an exponent, that is an instruction to write whatever the base number is, that many iterations is the word they would use, but clones, if you will. Right? So 2 times 2 times 2, right? Which means that this is really 1/8, right? And therefore, even if it is a little weird, right, as a coordinate, pair these two things together. You would have a dot, literally, at the location of -3, and then not even a whole number. You get a crummy fraction, 1/8. All right. Same thing here. If it's 2 squared, right, then it is the 2 iterations of the base number just coincidentally happens to be 2. All right. So 2 clones, if you will. All right. 2 times 2 is 4. So you would have the fraction of 1/4. Right. And again, if you pair these together in tandem, they are this dot, -2, comma 1/4. This one's a lot easier. This is just one iteration of 2, which is just the number itself, so a half. Right, and then you have a location of (-1, 1/2). When you have an exponent of 2, pardon me, you have a base number to the exponent of 0, all right? Because of arithmetic and because of rules of exponents, what you end up here is 1, right? Perhaps strangely. And then together you have 0, 1 as a coordinate. Virtually all exponential equations go through this point, all right? That's a keeper, do remember that, right? Sort of like in the other functions, if you had noticed, I'll just point at this for a moment. These functions, all right, have something in common, all right? The most basic type, that is the non-complicated, not transformation incarnation of these, go through the origin. 0, 0 is an interesting point for this graph, for this graph, for this graph, all right? For this graph, for this graph, all right? But not reciprocal. That's where the asymptotes would basically cross at the origin. But the one thing that these original 6 do all have in common is the point 1, 1. It's not drawn here, and I don't have a pen handy, all right? But remember that, all right? This line, all right, this diagonal line goes through the point 1, 1, all right? The parabola goes through the point 1, 1. The square root function goes through the point 1, 1, all right? This curve here for the reciprocal, 1, 1, also -1, -1. All right, cubic, 1, 1, all right, and the V shape, absolute value, 1, 1. Well, if those things have interesting points in common, 1, 1 in the origin, these exponential functions have this in common, all right, 0, 1. It's important, all right? Then there's 2 to the first here, all right? That is just simply 2. So we have the second point, 1, 2. Well, it's technically 1, 2, 3, 4, fifth point, right? And then this last one, 2 squared is 4. So you have a dot at 2, 4, right? What I'm going to do now is walk you through the experience of graphing these points that we generated by brute force, all right? Which always works, all right? Especially when you're trying to get a feel for what's going on here. So I'm going to take my little grid away for a moment and replace it with this white background here, and then strategically erase part of this. Right. Preserve the coordinates the ordered pairs that we just generated, and put the graph paper that I have underneath this. And then plot those points. That would be special effects. Not really. Ooh. Alright, let's see. If this is in the frame properly. Looks like it's okay, right? Could scoop that over just a wee bit. I don't want to make it fall off my ledge here. Okay. If you have a piece of graph paper handy, one thing I promise I will do is have available one of those coordinate planes that I already prepared for you, right? A blank, you know, it's just the axes in purple. What a nice grid to work with. I'm just going to systematically place these, literally these dots, right, in the correct position. All right, here's the first one. All right, at the location of -3, which represents an x value, I'm going to start at the origin, go back 3. So it would be 1, 2, 3, according to the increments here. All right, I didn't label them, but assume 1, 2, 3. Resist the temptation to leave a mark until after you have moved the appropriate amount of y. And bear in mind, you're doing this by hand, so it's never going to be perfect. All right, unless you really get out the ruler, right? And if it's 1/8, all right, it's not even a half. If one box up would be 1, leaving a dot here, you have to figure that 1/8 is just a portion of that, a fraction, literally. So maybe favoring the darker x-axis here at the location just above x equals -3, maybe make a dot just about there. Sitting almost just on the line almost. That's this first one. Right, now -2. Right, back at the origin, go back 2. Right, a quarter is like 25 cents. Right, it's still not quite a half. Right, it's just a little bit higher. Right, than 1/8. So at the location of -2 for x, just a little smidgen taller. All right, than 1/8. Put a dot here. All right. And then at -1, finally at -1, you can go just about halfway. And then right on the y-axis, because 0 is neither left nor right, all right, you can put the location of 0, 1 there. All right, I'm going to label that one, because again, it's an interesting point that these graphs, all right, tend to have in common. All right. Then there's over 1 up 2. And you see what happens now at this point. Once you get on into the first quadrant of the 2 up 4, 1, 2, 3, 4, there is a sharp turn. All right. Basically, what makes an exponential function, what is interesting about an exponential function is the behavior of this curve. I'm going to connect these because they really should be continuous. You'll see a sharp curve like this. Sadly, in the news, they keep mentioning, the mortality rates of the people who are getting sick, right? And they say it's exponential. It's true, all right? There is an application for this, even in medicine or in science or in engineering, all right? Not to, bring up a sad subject, but if it helps you remember, this is where that phrase comes from: exponential increase in sickness. Hopefully, what we want to do is get it to, start bending back down the other way. All right, in the long run. Anyhow, when you think exponential function, think this basic sharp curve like this, right? And similar to a reciprocal function, which is a type of rational function, it's not emphasized here. There are asymptotes, right, for a rational or reciprocal, right? Exponential functions have a horizontal asymptote, right, at the point of y equals 0, which is better known as the x-axis, of course. Right. So to illustrate that, maybe faintly in green, I don't know if I can show up well, in blue, right, I'm going to put a dashed line running like this. Right. It is sort of an imaginary boundary, if you will, where the graph will never go. Right. Your y value, in theory, will get closer and closer and closer and closer to the x-axis, but it will never touch it. All right. Mathematically, it can't happen. Okay. Let's see. So now it has a horizontal asymptote at this location, or along y equals 0, that imaginary dashed line there, and it has a y-intercept, all right, at the point 0, 1. These are two key elements to an exponential function. Important characteristics. All right. You know what I should bring up? I left it upstairs, so I'm going to go upstairs and get it, but a graphing utility, right? A lot of times when you're reading the homework, it says use a graphing utility. All right, we've had this conversation before. All right, I know that the criteria for the class was, you're not allowed to have a graphing calculator. To me, at this point, it's just kind of silly. So if you use the app, the free app that is Wabbit, it's not like Elmer Fudd, Wabbit Emu as an emulator for a TI-83 or 84, all right, that's fine. Or if you happen to have a graphing calculator, it'll make going through this process a little bit more fruitful, I think. Right? Why? Because then on the fly, you could just make the little alterations and see. Right? Being able to do something by hand is a worthwhile skill. You'll have a greater depth of understanding and appreciation for the subject. Right? But we're getting into the realm now where you want to do something a little bit more efficiently. right, if you can help it. Anyhow, I'm going to go get my calculator. Okay, and a little sip of coffee too. Here, just to get things a little bit, get them done a little bit faster, let me just show you with your calculator what this would look like. One slight little alteration. The graph that we have here is y equals 2 to the x, right? Where we have an input variable that is an exponent, we use some points, right? We just did some integers, right? In theory, this is continuous, which means the graph would flesh out the more points you generate, right? If you want to make a calculator do this, you have this type of calculator. It doesn't have to be a plus. It could be just a TI-83 or an 84, all right? Couple of things. Let me turn it on first of all. There's two buttons that you would use, y equals and essentially graph. The buttons that are in between are for reading specific points on the graph once it's generated, once it's drawn. That's trace. Think of these two, window and zoom, as being like an automatic and a manual transmission. Some people would prefer to have a car that is a manual transmission because they have greater control. That is a fair analogy, I think, for this calculator. If you wanted to, you could change the dimensions of the screen. That's all that this is for window. Zoom will do things a little bit more automatically. The problem with zoom, unfortunately, is that it doesn't always do a good job of it, you know. Anyhow, it does a lousy job. Let's do y equals. I'm going to clear out what I had in here and start from scratch. We have y equals 2 to the x for our base number 2. So I'm going to put 2, and then if you want to have the variable written as an exponent, this caret symbol here, upward pointing arrow, notice that it shifts. There's an intuitive space for you to put your variable x. And then this button, x tau theta n, fresh out of the box, is basically automatically x. You don't have to worry about switching it. All right, and you would just hit graph, all right, and you'll see it will draw the curve, same exact curve that we had, right? It's a little bit zoomed in, but notice where it went through. If you wanted it to read this point here and you hit trace, you could either move with the arrow keys, the little cursor, right, along the curve, or you could make an educated guess, right? It actually tells you right now. If you typed in any value, like say -3, is -3, it should give you the decimal equivalent, or if we're lucky, maybe the fraction equivalent, of 1/8 for y. Hit enter. 0.125 is 1/8, right? If you hit 0, it gives you the distinctive point of 1 for y. Right? Okay? And you can experiment with this. This is really the point. If you wanted to overlap graphs, superimpose one picture on another, especially if you had transformations. See what happens if you make this negative. All right? Here's 2. Upward pointing arrow. And then I'll use, be careful, if there's ever an error message, it's just probably because of this minus being confused with this negative here. For coefficients, use this button, even though they should be interchangeable, the software doesn't compensate. So you put negative, then you put an x, and then you have -x for your exponent, hit graph. And you see how this affects the picture, right? It just reflects it, right? Goes right through the same point, right? Okay, enough of that. Let's see. Moving on. Now, There is a handout that I made. It's not to be confused with the drawing that I attempted to do before. It's something that I had drawn a long time ago and then had the wherewithal to go, oh, maybe I should make a PowerPoint diagram of this. I'm going to let you see it now, and I'm going to refer to it probably in the forthcoming section. So like maybe comes up in section 8.2 a little bit later in 8.1, but more likely section 8.3 and 8.4. This is an overview of how to go about solving equations specifically. That is to say, if you had an equation that was exponential in nature, this is a list of techniques and what you would do in those situations, right? This is a list of techniques and what you would do in those situations if you have logarithmic equations. The one thing that is really important today is this situation, right? When you are given the same bases on opposite sides of equals, you're going to employ something called the one-to-one property. You'll hear that thrown around a lot, right? These other situations are more relevant when we do section 8.4 probably, all right? But you can have this right now and print it out, and I'll keep referring back to it. All right. Let's discuss using that. Let me get rid of this graph paper. And I'll rotate this again. And I'll erase this. So let's get into using the one-to-one property. I'm going to just write it like so. Like there are properties of exponents, there are properties for exponential equations and also logarithmic equations. And this thing gets mentioned a lot. What is the one-to-one property? It is basically this. If you have an equation, and you know if you have an equation, you'll naturally have an equal sign, where there are the same bases on opposite sides, then you could use something called the one-to-one property. And right now it's not really complete, but here's what the added feature would be. Right. If you have the same bases on opposite sides of an equal sign, then whatever the exponent is here, and I'll just make this, whatever the exponent is here, you could rewrite the equation as such. One can assume you have an equation like this, where whatever the exponent is on the left side, it is set equal to whatever the exponent is on the right side, right? And then solve this instead. Okay. Just make sure that whatever you're working with, first of all, that it's an equation and that you have the same bases. All right. If you don't have the same bases, you can't assume this. All right. If you do have the same bases, then you can assume this. All right. Here's an example. If you had an equation, and then we're going to translate it if necessary. See what you get. Suppose you had 9 is equal to 3 to the x plus 1. On one side you see a regular ordinary Arabic numeral 9. Right? On the opposite side of equals you see something that is a little bit more funky. Right? You have an obvious base and you have an exponent that is an algebraic expression. All right? If your problem, right, doesn't match initially, don't give up on it right away. It may be possible to translate it, which is why I drew this here, right? Try to translate into same bases. Why? Because if you can, then you could get away with using the one-to-one property. Okay? Now this 9 is not written as something that is an exponent, but you can rewrite it as such, right? Think of multiplication tables of 9. What times what makes 9? All right, famously 3 times 3. But what is that, right, as an exponent? It would be this. 3 squared is equal to 3x, 3 to the x plus 1. All right, now you have the situation where the bases match, just taking a little artistic license, right? Thankfully you could, because now you just need to pay attention to the tops. And you could solve this equation instead, which is so much easier. Right? And it's just a matter of manipulating, right? Subtract 1, cancellation effect. Your x value is equal to 1. Okay? It's written backwards, but it's no sin in writing it letter on the right side. Okay. Here's another example. Suppose you had something like this. I keep picking up that one. My least favorite marker, because it's so faint. Look at the difference, right? Fraction to a variable x is equal to 8. Right? Again, the bases, or what could potentially be a base, does not match what definitely is. Right? But it is possible that you could reinterpret the problem. Translate it. So I'll attempt to do that. Right? First of all, let's try to reinterpret 1/2. Right? I know that there is no exponent written here, but if one could assume that this was an exponent of 1, right? You may remember from the conversation before that the exponent that is a negative exponent would be this situation. Right? A negative exponent creates a reciprocal. Right? It makes a fraction, essentially. So if I just acknowledge that there really is a positive 1 here, and then manipulate it so that it is now on the same tier as this 8, that is technically above the line, rather than below it, all right? I could reinterpret this at least in terms of a base 2. Right? And at the same time, there is this 8 here. I could rewrite that also as being 2 to a certain exponent. And you have to remind yourself, multiplication tables. All right? What times what makes 8? 2 times 4, right? But the number 4 itself can be factored into 2 times 2, which means that overall, the prime factorization it would technically would be 3 2's, right? So this would be 2 to the 3rd. Now there is one little tweak also that I neglected on the red side here. There is a variable still here. And that's what I'm really after. I did successfully change this fraction to what the equivalent would be, but that's still inside of parentheses. All right, and there is still this x sitting outside here. You may or may not remember, I'm going to point to something from a while back. Rules of exponents. When you have the rules of exponents, you know that one thing you could do is raise an exponent to another exponent, in which case they multiply. And I lost my diagram here. Where did I put that? Very long time ago I gave you this. I had the same problem last week. Struggling to find a diagram. Bear with me. Let's always point at it. Just have it. There we go. Here. No, that's not it. Here it is. When you have a situation where you have an exponent raised to an exponent, this is known as the power rule. All right, remember, you can multiply them. That is really what's going to be happening here. What's 1 times x? X. What's negative 1 times x? 2 to the negative x is equal to, apparently, 2 to the third. Right? Now we have the ideal situation. They're the same bases, they're both 2's, so we really only have to pay attention to the tops here according to the 1-to-1 property, which means that this is going to be really negative x is equal to 3. Remember, it's not solved until it's just regular x. So, you're going to have this situation. You could just convince yourself, oh, that it has to be naturally negative 3. We'll put the coefficient of 1 and then manipulate it by opposite operations. Divide by negative 1, divide by negative 1. There's a cancellation effect. And it's very faint. My green's always like that. And then you just end up with this. Positive 3 divided by negative 1 is negative 3. That is what your x value is. All right. Now let's see. Let me do one more of these, and then we'll switch gears here. Suppose you had eight equals 2, and then the algebraic expression was a little bit more complicated. We're still going to try to do the same thing, the same strategy, which is to reinterpret this regular number as something that is the same base, right? Because that will allow us to perform or apply the 1-to-1 property. We already know that 8 is really 2 to the third. That has been established. Now that we have the same bases, we really have to pay attention to the exponents. And we can solve this equation instead. We can do 3 is equal to 2x minus 1. And what you end up with is going to be a 2-step algebraic equation, so no sweat. We manipulate it like we would normally. Do the easy part first, arguably the addition or subtraction part. Right? So opposite of subtracting 1 is adding 1. Add 1. There's the cancellation effect. This is left over, 2x. 3 plus 1 is 4. Right? How do you get rid of 2 if it's a coefficient? It's understood that these two things pressed together being multiplied, so you would divide by 2 to cancel, and do the same to the opposite side. That means that your x value is equal to 2. It's kind of satisfying, right? I think so. All right, moving on. All right. Let's discuss transformations. Okay. Let's see. Transformations, there is again a diagram. I think I gave you a long time ago. I'm going to flash it. That looks something like this, right? This table here. I'm basically just going to reinterpret. You'll have a blank, all right? And I'm basically going to relate the model that we had for transformations to this new stuff. So if you're inclined to print that out, that would be cool. All right, I'll give you an example of what the effects are. All right, let's see. I don't have a predefined tablet here. Now, I missed my projector that we have in class because at least I can superimpose it onto the board and then kind of fill in the diagram, but hey, whatever. When we consider transformations now, which are little alterations that you make to a graph, basically. Remember, we had a model to work with. So I'm going to draw this. Here's our original model, which looked like this. First of all, it was in function notation rather than y, but same difference. So you'd have an italicized f, parentheses, and an x. And then there are these key features. Let's see, put a b in here. bx minus h plus d. It was these key components, right? A negative causes something to flip, essentially. They call that vertical reflection. The value that is here, the factor that is up in front of the parentheses, is a vertical stretch, all right, or compression. In your textbook, they refer to this as shrink, right? I kind of like compression. The factor that is here is similarly a horizontal stretch or compression. And more likely you'll see a number written here or here. That's usually the extent of the transformation for the easier type of problems. This is the horizontal shift, and this is the vertical shift. This is stuff you had seen a while ago when we first broached the subject. All right? Just beware. All right? The number that is sitting in this position, right? And just think of these as being 4 or 5 jobs, these positions in your equation. All right? The one that is the horizontal shift is counterintuitive. So when you see a negative number here, your intuition would naturally be, well, I was taught that negative means either going down or, in this case, horizontally moving towards the left. Just realize that it's counterintuitive, and it will be like that for virtually every transformation model that you see, whether it's adapted for linear functions or something more complicated. All right, whatever is sitting on the inside of the function, just think of it as being opposite sign. All right, now why call it h? And actually, I should say the original model was k here. All right, why call it h and k? I'm not really sure. H is in horizontal, right? K is something that makes the same sound as C, and C is in constant. This is usually just a number here. Perhaps that's the reason. Anyhow, more importantly, know the jobs. All right? And that whatever number you see in this position, this position, this position, this position, or this sign, that's what the effect will be. All right? That's the old model. All right? We'll have an adapted version of this, specifically for exponential functions. So this is the new adapted model. Let's see. Still f of x for function notation, but because of the nature of exponential functions having something written in superscript, you're less likely to see parentheses as in something that is linear or potentially even square or quadratic. What you'll see is this. Some plus or minus some factor up in the front, but then features like these. For some reason, in a lot of textbooks, when they get to this point in the conversation about transformations, they drop the h and the k, and they just, even though these are the same jobs here and here respectively, they use c's and d's instead. That's why I inadvertently wrote d already. I was jumping the gun. All right. Anyhow, just to remind you, all right, these features, all right, correlate, right, to some job, basically. Right. I have to kind of tell people to be quiet. Pardon me a minute. Anyhow, I'm going to have you fill in the table now where I describe the effects of these, whatever number is sitting here, number sitting here, here, or here. Okay? Anyhow, that's what the model would look like. Something where there's an obvious exponent, or something that is in superscripts. Okay? In the sheet that prints like this, I'm going to try to replicate that as quickly as I can. Let's see. Here, I'll break out the ruler again and draw this. Owie, that hurts. This isn't going to work out too well. Too heavy and limp. Alright, something like that. Okay. That's good enough. Frame. Looks like it's okay. All right. The three basic transformations that you have are shifting, reflecting, and stretching, compressing, or shrinking. Stretch, like I'm doing now. Compress, which is another way of saying shrink in some context. Okay. And beneath that are sort of subcategories, if you will. There are these. I do kind of need a ruler again. Let me see, there's a smaller one would be great. Go all the way across, but maybe I'll compensate. There you go. It's a little crooked, right? Yeah. Oh well. Low budget math. There is vertical shifting, which I'm just going to abbreviate as vert. And there is horizontal shifting, which I'll just abbreviate as HARS. And the same thing here, there's vertical reflecting and horizontal reflecting. And there's vertical stretching and compressing, and there's horizontal stretching and compressing. Shrinking. One more. I've tried every ruler that I have here, and none of them are great. Well. Put that there. Must have lost it. Not to waste too much time, but bear with me. Because neatness helps in math. That's one thing I've not learned the hard way in my life. If you have good, neat handwriting, that makes you less likely to screw up a calculation. So, English class, elementary language arts skills, cross curricular. The letter in question that controls vertical shifting is D. Let's see if this shows up on the frame here. Right? So whatever is sitting in the model in the D position, know that that is going to cause a vertical shift. Right? Similarly, what is sitting in the C position, that will cause a horizontal shift. When you have a negative up in front of the letter A, I'm just going to make this the coefficient up in front, that causes a vertical reflection, which means it'll be reflected over the horizontal, the x-axis, somewhat, perhaps ironically. When you think vertical, you don't think of x's, but it's the x-axis that causes a vertical reflection. If you have a negative attached to the x variable, that causes a horizontal reflection in this case. Okay. Then there's A and B, right? Which causes a vertical stretch. The A, whatever number is sitting in the very front, right? Well, if it's a whole number, right, you'll see a certain effect. If it's something smaller than a whole number, like a fraction, you'll see a different effect. And what causes horizontal stretching and compressing? B, the actual base in this case. Okay, so look for those things. See if I can get this all close. Just a one shot would be great. All right, close enough. All right, now let's do some examples and some drawings. Okay. I'm going to squeak this in here. Suppose, as an example, you had the most basic function, y, that is exponential, to the 2x, y equals 2 to the x. All right, we had seen before, here's the simple picture. You have a graph that basically looks like this. Right? That goes through the point 0, 1, and it curves up like this. And there's a horizontal asymptote. Like so. I'm trying to, I should use a different color, but the horizontal asymptote runs along the x-axis. So I'm going to try to make it dashed. Like so. Okay. If we just tweak this ever so slightly. This picture, and we throw in one interesting feature. Still y equals, still 2 to the x, but I throw in a d value, in something that is in the d position. It's a number, a term, that is a whole number usually, added or subtracted. So if you see, let's just say hypothetically +3, the effect on the drawing is that it's going to be shifted vertically. Right? This is sitting in the D position. In terms of a graph, here's what you would see. If normally, and I'll put this in blue, here is where the vertical asymptote, pardon me, the horizontal asymptote is, y equals 0. And what this is going to do is shift everything, including the asymptote, and I would start with that, up 3 increments. So 1, 2, 3, and now you have a dashed line running horizontally here at y equals 3. Instead of your graph going through this coordinate of 0, 1, that point that is 1 will have, you'll add 3 to it naturally, which would make it 4. All right? So you'll have this point instead. And we'll just put this in blue. You have the exact same curve, and it runs up a little bit higher. Right? And this point would be 0, 4 instead, through there. It's more effective of the sloppiness of my drawings here. I have to try to do something like this with your calculator. Right? But I just want to show you the tweaks one by one. If you just use your calculator basically to experiment, right? Go back to y equals, here is the original function. I'm going to go down to this one. Yeah, I erased it. 2 to the x, and then this one will clear out. I'm going to draw 2 to the x again. But then throw in the 1 transformation, plus 3, and then you'll see the 2 pictures once they are graphed, once they are drawn, superimposed on each other. There's the original one. And if you don't see the next one, notice that there's sort of a little timer over here. It just means that the dimensions of the calculator have to be shifted. I'm going to use automatic. So I'm going to go to zoom. And if you go down this list, Z standard is a good place to start. That's a 10 by 10 graph, basically. But I'm going to go to zoom fit. Right. And it will sort of give me an ideal picture, hopefully. There we go. Nah, I don't like that. That's crummy. All right. And it's drawing the other one. That's why it's taking so long. If your calculator doesn't do anything after a minute, that means it crashed. I'm going to try Z standard here. This might be a little bit more satisfying. There you go. It doesn't draw the horizontal asymptotes, right? You could get it to do that yourself by putting y equals 0 and then y equals 3 would technically be. But this is the first original curve and this is the second transformation curve. Okay. In this space, although it's a little bit exaggerated here, let's see what happens when you throw something into the C position. Okay, if you have y equals, same base, but you have 2, and then the exponent is x plus 3. All right, remember, the C is the one that is annoying because it is counterintuitive. Which means that if you see a positive, treat it as negative shifting. If you see a negative, treat it as positive shifting. All right. Here is a simple coordinate plane. All right. This is, again, the original graph in red, and the transformation graph, I'll try to do it in green, right next to it. If it's shifting horizontally, all right, it's still going to have the same asymptote that runs at y equals 0. All right. But instead of the graph going through the point that is 0, 1, all right, it'll cross the y-axis somewhere, and you could calculate that by putting 0 in here, but it would be at the location of, looks like it would be 0, 8 instead. Anyhow, what would happen is that, being counterintuitive, and you know it causes a horizontal shift the picture from here, all right, over 3 increments to the left, ironically, because it's counterintuitive. So 1, 2, 3, you would have a dot here, right, and then your graph would look like this instead. Right? It's still on the same level, right? in terms of the horizontal asymptote, and the curve really isn't deformed at all. It's just scooted over. So you would be at this location instead. This dot, that is the originally 0, 1 dot, in respect of the shifting, is at the location of -3, 1, as opposed to 0, 1. Okay. Vertical shifting. I'll try to do this a little bit faster. All right. If you had just this one slight alteration, you put a, let's see, a negative out in front of the exponent. Notice something. Here's the original function. Here is that one slight alteration, that transformation of a negative in front. Notice that this negative is not grouped. There's no parentheses around the 2. All right? It's just as an afterthought. The effect that it is applied is a negative. The effect is that your graph will look like this. Right? You will have the same horizontal asymptote, right? But it will be vertically reflected. So if your point is normally 0, 1, what you'll end up with is 0, -1. And the graph will run this way. Use a different color if I can help it. Down. Downtown. Okay. It is vertically reflected. So rather than this, it is vertically reflected over the horizontal axis. Okay. Let's see. All right. What else can you do? Well, here's the next thing. Horizontal reflecting. You put the negative in a different place. Right. Here's the base of 2 again. But I'm going to put the negative attached to the x. So it will be up here. Right? That, of course, doesn't make the values negative. It just makes reciprocals. It will make fractions when you have a negative exponent, right? So in terms of a picture, how would that look? Pardon me, I got to answer the door. So you have a negative. This is the effect on the graph. Right? Still same horizontal asymptote. So you'll see something like this. Right? And it will in fact go through the same point, right? Which is that point of 0, 1. But the graph will be horizontally reflected. So if something is horizontally reflected, it's reflected across the y-axis. Right? And you'll see a graph that now runs this way. Okay. Let's see. The compression and stretching is a little bit more complicated. All right. So let me draw you 2 examples here. All right. I may have to scoop this over. Let's see. Suppose you had y equals, and I'm not being too creative here. I'm going to separate out the original function features of 2 to the x into a parentheses. That's this chunk, right, like so. But I will put the next easiest number that I could use after 1 is 2. Right? So I'm going to put a 2 here. All right. Notice because this is grouped, all right, that it's not until after the exponent is applied that you would multiply by 2. So if you had 2 to the first, yeah, the inside guts here would be the amount of 2. And then it would be 4 from multiplying as an afterthought. But if you had 2 to a negative, you know, or something like that, you'd end up with a fraction times 2. You know, so make sure that you would deal with this portion of the equation first, according to the order of operations. Right. Anyhow, here's how your graphs would look. I'm going to do 2 of these. The original curve goes through 0, 1, and would look something like this. If the A is something greater than the number 1, right, then this is what you would see. Let me put this in blue. If A coefficient is something greater than 1, it's going to be deformed vertically, right? So you'll have something that looks like this instead, right? It'll be stretched vertically. If you have this situation where your A value is greater than 0 but less than 1, meaning that you essentially have a fraction as your coefficient. And I'll draw this as an example. Let's say that you had 1/4. In contrast to, again, the original function would look like this. Goes through 0, 1. What you would get is something a little bit flatter, vertically flat, compressed vertically. Your graph would look something like this. I'll put this in blue again. It would be squashed vertically, which you would say is compressed, vertically compressed. Right? This is stretched. This is compressed. That was the last one. I have a similar issue here. There's really two possibilities for each of these. Stretching and compressing. I'll give you again the most basic example. Something like this. Where you have the base number, I'm going to purposely write in parentheses, is something like this. Where you have the base is something greater than 0 but less than 1, so in theory a fraction. You can put a decimal if you really want. This is how the picture would look. I'll leave space for hopefully the next one. If this is, again, the original goes through 0, 1, then your effect would be this. It actually looks very similar to a horizontal reflection. And here I'll show you with a calculator. Here is the original function. I'm going to just tweak the second one here. Clear that. And then do this. First of all, the horizontal reflection. So I'm going to put 2 to the negative x. You see that typed like so. This is why it's great for having a graphing calculator. You can experiment. There's the original function. Here's the horizontal reflection. I'm going to do the same thing now. I'm going to keep the original function, 2 to the x, but I'm going to make that one little tweak. I'm going to make the base number half. So I'm going to put this in parentheses, 1 divided by 2 is the x. And you'll see what the effect is. Here's the original function. And here's changing the base. That has basically the same effect. Okay. If you have this situation where your base is greater than 1, We already have 2 to begin with, so let's do the next number after 2 would be, the next integer would be 3. If this is the original, goes through 0, 1. Using a different number, it ends up going through the same point of 0, 1, but it climbs a little bit more sharply. Right. This is when you have it compressed. Horizontally compressed, it's squeezing it in this orientation. Okay. All right. That's a summary. All right. So again, look for those key points. All right, where the negatives are, where there's extra numbers that are terms. All right. Where there are differences, some change to the factors. All right. Quit that. About an hour and a half in. All right. Let me show you one more thing. Let's see. Let's talk about E for a moment. I may have to wash this. Sometimes when you don't erase fast enough, it gets a little bit stuck. If you look at my reds, they write nicely, but they don't go away. Spray here. I may have to get some paper towels and then come back.
Sorry, that was also.
No, that's okay. Helps. I'd like to get different colors than I have, but it's kind of hard to come by. Staples isn't that open enough. Not sure that it's open at all, actually. You have to order it. And then I may stop and then film 3, 2 as a separate video. And we'll see. I'd rather not do that, but we'll see. Alright, there is another handout that looks something like this. It will be a blank sheet. Alright, what I would use this exercise for is just to introduce you to this concept of E. Alright, now as a quick rundown, and we use E sometimes as a base number, that's why I mentioned it. E is an irrational number. You know that numbers, if they have something of a family tree, can be organized like so. First of all, there is real numbers, and then there are imaginary numbers, which are not really relevant right now, but that would be the first sort of dichotomy of things that are real, right? There are rational numbers, all right? And then there are irrational numbers. Pardon me a moment. Recording. Okay. Sorry. Irrational numbers are things that can be a fraction. All right. Irrational numbers are essentially things that can't be a fraction. And famously, of the irrational numbers, there are 3 that you know, or at least 3. There's famously pi, 3.14159. The square root of 2, 1.41, I think it's 42, something into infinity. And then there's this next one, e. All right. 2.7172 something into infinity. Oh no, not 7. Pardon me. 2.71. I think it's like 82 after that, actually. Anyhow, when you're a kid, what do they make you do? They make you memorize pi up to 2 decimal places, 3.14. Square root of 2. But if you were going to incorporate this as part of some calculation as a decimal, it would be like 1.41. And similarly, e, 2.71. All right. Anyhow, where does it come from? Well, pi comes from the attempt of writing a fraction. All right. It's a futile effort, of course, but it's the fraction that is the circumference of a circle divided by its diameter. All right. For any size circle, those two measurements divided seem to have this relationship. This number keeps showing up. All right. If you can measure more and more precisely, all right, you get a longer incarnation of pi. But it's an irrational number, so it really will never be a fraction, really. All right. This also comes from geometry. All right. Square root of 2 comes from Pythagorean theorem, basically. All right. A squared plus b squared equals c squared. E comes from finance, right? So in terms of time, right, these are from ancient times, you know. This comes from maybe like the 1600s, you know, 16 to 1700s, right? And it is from finance specifically. Whereas these are from geometry. That's sort of an overview. All right, good to know. These are, as somebody else has said, and I really like this, these are the superstars, if you will, of math, right? The constants, they call them. Mathematical constants. The diagram that I would have given you illustrates how you would produce E. Right, as I said, it comes from finance, but let me point at it in this case. All right. If you took this formula, right, 1 plus 1 over x, and then raised it to the same number as an exponent as whatever the denominator is, if you did this calculation for several numbers, here's what you would see, right? For 1, all right, if you put a 1 here and a 1 here, it would be 1 plus a half, basically, in which case, let's see, is that correct? 3 over 2. I think that's an error, isn't it? Let me double check. Why do I feel like that's wrong? Oh no, what am I saying? Forgive me. Yeah. Alright. If you put a 1 here, right, it's 1 over 1. I'm thinking of a half. I'm reading it backwards again. This is my camera. Alright, 1 plus 1 is just 2. Right? 2 to the first is still 2. Right? If you now put the number 2 in here, all right, insert this as your input number, value, it'd be 1 plus a half, right, which is 3 over 2. That would be 3 over 2 squared, right, in which case this is the result to get 2.25. If you stick 3 in here, it'd be 1 1/3, right, so 4/3, right, 4/3 cubed would produce this repeating decimal, 2.370, I want to say. 4, then you get, it's longer, right? I don't think this is repeating. I think at this point it's becoming, it terminates in this case. 10, all right? 1 plus 1/10 to the 10th, all right? Then magnitude of 10 squared, all right, which is 100. You get this longer and longer number, 1,000, 10,000 is your input. This is the effect. The numbers start to stabilize up in the front digits, right? And you get 2.7181, and it gets longer and longer and longer. And you could do this forever and ever and ever. Right? This is basically the basis of calculus, or at least one portion of it. All right. This is what I was alluding to here. The limit as x approaches infinity. All right. Produces famously this number e. It's just a coincidence. Euler was, I want to say, a Swiss mathematician. His last name started with the letter E. I don't believe that he so arrogantly said, "You know what? I should name this after myself." Perhaps people after the fact said, "Hey, you know what? Perhaps we should honor that guy." He did contribute a lot. This is what the graph looks like. All right, it's an exponential graph, so it again goes to that interesting point 0, 1. All right, but the next point after that would be at the location of 1 would be e itself, 2.71 technically. So it rises perhaps a little bit more sharply than say 2, you know. All right, and it has a horizontal asymptote. You could test it, like if you print this out and you plug in these coordinates into your calculator, you'll see that number shows up, all right, eventually. All right. Now, of exponential applications, right, let me give you this diagram is sort of an overview again. Right. There are some formulas that are useful. Applications, I can just spell. All right, there's an exponential formula that's for population growth. And an exponential formula for compound interest, which is again finance. And another one famously for the mass of a radioactive substance. And more or less a generalization, right? They call continuous growth or decay. Bear in mind, these are all some form of an exponential equation. They're a formula, which is just a practical equation. All right. Population is an example of growth. All right. Compound interest, ideally, should certainly be growth. Mass of a radioactive substance is an example of decay. So the graph would basically, instead of being a curve upward like this, in respect of the coordinate plane, these are growths. When you have behavior that looks like this, decay would be something like this. Something that's diminishing over time. In theory, a radioactive substance, and bear in mind, virtually everything that is natural is radioactive to some degree, not life-threatening, but everything is radioactive. Right? Over time, and in some cases it could be millions of years, all right, the substance will actually change into a different substance, right? Like for instance, radioactive substances above lead on the periodic table eventually transmutate into lead. They stabilize, or the majority of the particles from which they comprise turn into lead. Let's see. Now, what do the formulas actually look like? Here, let me put these in blue to start with, and then what I really should do is just describe what the individual terms correlate to, right? For population, right, a lot of times it's written in function notation, so you'll see a P and then a parentheses and then a T, right? All that is saying is that it's population as a function of t, right? So as a function of time is what it is. You could just as well see it as just a capital P by itself. On the opposite side, you might see a little naught symbol here, so P subscript O, right? Parentheses 1 plus R, and then a T here. This is used to calculate the growth of, say, something like bacteria, all right, left in a petri dish under ideal conditions where it has some source of food, all right, or way of making some food, you know. The conditions being right. But what do these other things mean? P naught is the initial population of something. So basically the starting population, if you will. R is the rate of change, which is basically the percent that is quoted to you. Just bear in mind, if you have a percent, you would have to take that percent, if you're going to use it, and convert it to a decimal, which just amounts to moving the decimal place twice to the left. All right, so if you got 3%, it would be 0.03. It's like you divided by 100. Percent literally means per 100 or divide by 100. T is intuitive. Lowercase t is time, except that it has to be in years. Right. At least to start with. I mean, there may be some modifications you could do perhaps, but that's what you would expect. All right. Compound interest looks like this. Again, it might be written in function notation, so you might see a parentheses t. That just means that it's a as a function of t, just like population as a function of t. A, or just capital A by itself, is P naught, and then a slight tweak of this formula is 1 plus R over N to the nth times T. It's unfortunate that a lowercase r kind of resembles an n. They're not the same thing. That's an n here and an r here. Okay, and there's also another n here, and this is a t. All right, what do these mean? Well, P naught is principal, is what they refer to it as. And principal is essentially an original amount of money. Money that is invested. Right. Or, and if you're talking about in the context of a loan, it would be borrowed, right? In which case the bank is looking at you with dollar signs and going, "You are my investment." And the joke's on them because I'm a bad seed. I didn't pay my phone bill today. Okay. Let's see. R is again the rate, right? Which again is given as a percentage, which means you have to convert it to a decimal. N is number of times compounded. Now that warrants explanation. Let me put this up here. Unfortunately, I'm running out of space. I'm just going to put this here, and I don't want to erase that. I'm just going to put that back. Continuous growth. All right. What does it mean to be compounded in general? Basically means applied as part of a calculation over and over. Right, so if you have compounded interest, there's the original amount of money and then the interest is calculated, but then the sum of those things is then applied to the formula, right? And it may happen several times if it's programmed that way, right? If a person is, an investor, not just simply somebody who's borrowing, you would want something to be compounded as often as possible. When I'm going to give you a word problem as an example when we get there, but continuously compounded is to your benefit versus compounded maybe once or twice a year. Then there's again T and time in years. Okay, So the original amount of money is just referred to as principal. It unfortunately shares similarity to P here for population. R is still a rate, it's just the percentage quoted to you. N is the number of times compounded, and compounded is referring to how often something is applied into the calculation over and over again. All right, and T is time in years. All right, now there's radioactive decay here. One example I have of decay, which I'll put in a different color again. The formula looks like this. Again, it might be written in function notation, so you might see it as A of t. A as an amount, or A as an account. It's used as an account, or a dollar amount, all right, in this context. And A is used as an amount in the context of an amount of substance, in this case. So one is money and one is mass. All right. Anyhow, the formula looks like this. A naught, 1/2, and then T sitting on top of N. That's got a little flair there. Right? All right, what do these mean? Let me put this in a different color here. A naught is the original mass of a substance. Really messy, I'm sorry. Substance is, I swear what that says here, substance. T is time in years again. Right, and N is referred to as the half-life. Perhaps you have heard of that game. Right? I've never played it myself, Half-Life. It looks like one of those post-apocalyptic future kind of games to me, right? Like, what is more, there's another one that's kind of like kind of ironic, the animations and aesthetic of it. Fallout, right? Half-life is the amount of time, let me put that here. Half-life, the amount of time it takes a radioactive substance to reduce in mass by half the original mass. Now, as I mentioned before, and I'm no expert, basically, if you have a radioactive something, right, and you kind of think of something like plutonium, really, something lethal radioactivity. The reason why something like plutonium is such a terrible thing, and it's a man-made substance, plutonium, I believe, right, is that it takes a very long time for it to go away, right? So if you have plutonium-239, I want to say is the radioisotope of plutonium that is used in a reactor, potentially a weapon. Even if you destroyed the Earth with a bomb that had plutonium, all right? The plutonium is going to hang around even after the explosion, right? And it may take thousands, if not millions of years for the plutonium to basically disappear and convert into some other substance, because radioactive substances above lead on the periodic table, which I want to say is 82 protons, all right, eventually decay. They turn into lead, right? Not to digress, but an interesting thing. In the Middle Ages, the alchemists, these are people before chemists, right, existed as a vocation, used to be obsessed with turning things into gold. And the mistake that they had basically made is that they thought that they made things into gold by simply changing the color of whatever substance they were working with. Like they basically electroplated something without maybe realizing it. So they took the particles from say tin and like put them on something that's not that color, and make it like have a yellow hue. Zinc is yellow, I want to say. Anyhow, I think zinc is yellow. Anyhow, you can't by chemical means change the identity of a substance from one element into another element. You can, in theory, and I've never seen anybody do it, radiologically, right? By some kind of nuclear physics, in theory, change a substance from one element into another element. But there's a tremendous amount of energy released in the process, and it's usually not controlled very well, So in theory, if you could somehow, with some kind of precision, start plucking off protons off of lead, you could make it into gold, right? It's a couple of protons lower on the periodic table. Anyhow, that would cause a radioactive situation. Anyhow, radioactive substances over time lose their mass. They basically turn into something else, right? They're no longer the original element, right? And half time is the amount of time that it takes, right, to do that, to reduce by the amount of 1/2, right? And this is the formula, right, which, as you can see, is something that has an exponent. T is time in years, and N is the half-life. It is essentially the rate at which that happens. As for continuous growth and decay, this is more of a generalization. You have this formula. Again, if it's in function notation, it might be A of t, or just simply A again. And it would be this. A coefficient, right? The number E as your base number, and then R times T is your actual exponent. All right. Lowercase a is again the initial value, whatever it is referring to. R is the rate again, so it's a percentage. Right. And T is time. Time does not have to be in years though. All right. I don't believe. Right. Anyhow. Oh, it is in years, I'm sorry. All right. So A, R, and T for time, which I should do like this. So those are an overview of the formulas that you might see if you had a word problem. I'm going to do one word problem just for the sake of experience, give you a warm-up feeling about this. Okay. Okay. There is, again, a handout that looks like this is an example of a word problem. This is 143 for our section. All right, word problems, and we'll do this together. If you want to print that out, work right on it. Okay. This is in relation to population, so I'm going to try not to erase this. No, actually it's this. It's compounded interest, because it's money. When I think of money, it's interesting. If only we had some, right? Let's save the compounded interest, the continuous growth formula here. And I'll rewrite compounded interest over here. This is related. Put this in blue. A is equal to P naught 1 plus R over N to the NT. Okay. So we have these two formulas that are related. I'll just draw this really quickly. Here's the word problem example, right? You invest $12,000 at an annual rate of 3%. Find the balance, the account balance after 5 years. Right, given those conditions for each type of compounding. This is me taking a little artistic license. Right. When I make my handouts, I purposely put the things that are the numbers involved in different colors. Green as in money, right? That makes sense. Just for distinction here, I put the percentage as in red, and I put the amount of time in blue. It doesn't have to be those specific colors, but when you're reading a word problem, a good strategy is to normally circle the numbers. You may not end up using all of them, but if you had to craft an equation from scratch, or even if you had to fill in a formula, that is, you didn't create the equation, you borrowed one, all right? At least your eyes will be automatically drawn there, all right? And then you could kind of like consider each one individually and say, well, is this just meant to throw me? Because sometimes they're written that way. Or is this really truly relevant? Right? Anyhow, these numbers are going to be used. No tricks here, right? 12,003% in the style of a decimal in 5 years, right? The first part of this was figure out what is the account balance quarterly, figure it out monthly, and then figure it out continuously, which means we're going to switch formulas. All right, if you did it quarterly, I'll put that here. And monthly here. And then continuously I'll put here. For these two, I need the compounded interest formula. For continuously, I'm going to go for this incarnation of an exponential formula. So, in this case, the account A, right, will be the initial value, that's 12,000. I'm going to put that in parentheses as if it's a little pocket that I'm filling, times, so it's pressed together, 1 plus the rate in the style of a decimal, 0.03 over the number of times something is compounded as the end value, all right? If it's compounded quarterly, all right, compounded quarterly means every 3 months, all right? So if you took a year of 12 months and you divided it up into 3 months each, all right? Quarterly means that it's going to happen 4 times a year. This calculation will be done 4 times a year, and the amount of money that is accumulated will be reinvested entirely. So you're going to put a 4 here, all right? And then in the same place up here, 4 times 4 for n in the same n that is here and here, and then times 5. All right. If you wanted to kind of simplify this before you type it into your calculator, all right, you would basically have this 12,000. All right. The way that the 1 plus 0.03 over 4 would work out is that it would be essentially 4.03 over 4. How come? Because if you treat this like fractions, I know there's a decimal involved here, 1 whole is 4 over 4, all right? And then you add the tops. 4 plus 0.03 is 4.03, keep the same denominator. And then reduce this, well, combine this, 4 times 5 is 20. What I'm getting at is you probably would want to type this, including the parentheses, all right? And the value that you'd get is an approximate. You'd get something like, if you're rounding to the nearest penny, $13,934.21. So So it's not bad, all right? If you could, imagine you were fortunate enough that he had $12,000, it would be great, right? But in theory, this is why people who are wealthy to begin with make money without struggling, because they have money to play with, right? That should be the goal for all of us, I suppose, right? That you have some money to play with, and then don't gamble it on the stock market, right? Put it into an account that does compounded interest if you could find that, right? And then sit on it, right? After 5 years, you'll have made almost $2,000 extra. It's hard not to, to touch money, especially in the case of an emergency. But that's an ideal situation. If you did the exact same calculation, but you did for monthly compounded, all right, then this is what the calculation would work out to be in red in this case. It would be A, the same number, 12,000, but in here, it would be 1 plus 0.03 over a different denominator, all right? N is the number of times, would be the denominator here, that it is compounded. If something is compounded monthly, how many months are there in a year? 12, right? And then that makes this 12 times 5 over here. If you want to sort of simplify this as best you can before you start typing into your calculator, it might look like this: 12,000 times, again, to combine these would be 12 over 12, 1 whole is 12 twelfths. All right, and then you would have 12.03 over 12. And then 12 times 5 is 60. You would type that. Okay, in which case you'll see this as an approximate in terms of money. It'd be $13,939 and about 40 cents, rounded to the nearest cent, which is also very nice. All right, not much of a difference, but you made just about $5 more. Notice that's $934 and this is $939. Okay. Now you'll see if you just use a different formula entirely, and I suppose if you were in the position of authority, you could do whatever you want. And frick that, I'm gonna use this formula again. Cha-ching! All right, see what you get. We'll use this for continuously compounded. A, E, R, T. I'm just gonna superimpose the values here. The A value is the initial value, which means that this is 12,000 again. This. The E is just what it is. E is E. You don't have to type that. There's a button on your calculator to do that. And it's more precise than simply rounding it to 2.71. No sin in doing that, especially if you're using a cheapy $5 calculator. But if you have a scientific calculator, or if you have a graphing calculator, or the emulator, all right, there's a button for this, and I'll show you. R, all right, it is 0.03 in the style of a decimal, and then 5. Right? So you would basically type this, all right, 12,000 times E, and then up in the parentheses, you're going to use the caret symbol in this case, you would have that. Right? If you wanted to, you could simplify this yourself. All right, 3 times 5 is 15. So this would be 0.15 really, is what is here. Now as far as typing is concerned, let me show you. All right. Home screen. Okay. I'm going to be a good guy and put these parentheses. You can, in many instances, get away with not doing that, but I think it's better safe than sorry. This isolates that value. And it's performing that job, all right, times E. As far as E is concerned, it's behind the division, I believe that is correct. Yes. No, I'm sorry, wrong. Was that the right E? Yeah, it's E, all right. There's in 2 different places. I'm gonna go with the natural log one. If you look LN here in blue, all right, you have to hit second first, and then hit LN, and you see E shows up, and there's a natural place to put the exponent that you choose. I'm going to use the outcome of 0.15. So decimal 0.15, and then scoot out of there. All right. And then you're on the main tier, and you hit enter, and then you see what you get. Right, the account value in continuously compounded instance is $13,942 and almost 1 cent. Right. So this is rounding now. This is definitely involving an irrational number, which is infinitely stretching, so you're going to have to round at some point. Anyway, go with your calculator's high degree of precision, and you get a better answer. 13,934, 13,939, $13,942. All right, so what are we to learn from this? Basically, you want to have your interest continuously compounded when you're trying to make money. All right. All right. And that is the end of section 3.1. Another 2 hour and 15-minute mark. All right. I'm going to try to go a little faster for the next one. And now we'll stop. Section 3.2. This is section 3.2, which is about the inverse of exponential functions, which is logarithmic functions. Logarithmic functions and their graphs. Get down, get funky. Okay. Now, one point for the sake of clarity is this word, logarithm, right? Where on earth did this word come from? Hopefully this is still in the frame. There's a famous mathematician known as John Napier. Napier lived in, I want to say, the 1600s, something like that. And he was a Scottish fellow. I believe that's how you pronounce it, Napier. That's the only way I've ever heard it. I've read it, mostly. He, like a lot of people at the time who were educated, if you went to college, one thing that you were guaranteed to learn is Latin and Greek, right? And if you were lucky enough, Arabic. Probably if you went to school in North Africa, which at this time is definitely a better deal because you would be learning the math from the source, right? Algebra itself is an Arabic word, right? It is borrowed, the techniques are largely borrowed from India, all right? But by way of North Africa, all right? That's how it came into Europe, and rather late by comparison. So Napier, who was a Scottish mathematician, right, incorporated what he learned in his other classes. So he probably learned Greek, all right? Just so happens that the Greek word logos, right, means numbers. Or something akin to it. And then there's arithmos, right, which refers to ratios. All right. So, what is a combination of these two, logarithmos, all right, ratio of numbers, right? It's a slightly different context, all right, than what we think of a ratio of numbers nowadays being a fraction, right? All right. But if you think of a ratio not as being a fraction so much, but a little bit more literal as being a number on top of another number, that's to get you a feel, right? Perceive a logarithm as basically that, right? It has to, since it's an inverse of an exponential function to begin with, all right? This is very faint. A ratio of numbers in the context of logarithms is not referring to a fraction, that is this, a number sitting on top of a number like that, using this line. It's a number on top of another number in this context. There's a base, and then there's a number sort of on top of it next to it. There's just no line here, you know. Anyhow, it does have a different job than fractions, certainly, right? but it's derived from the same words, logos, arithmos. I think I have it backwards, actually. Yeah, I'm sorry. So much for my Greek. Somebody who's a Greek-speaking person is probably going to slap me now. Logos, that is ratio, right? And I think arithmos is numbers, but I mean it the same way, in the same context. A number on top of a number. In this context rather than in this context. All right. Let's see. Okay, now to summarize, let me give you this. I have to look that up. That's gonna bother the heck out of me. See, the one way or the other. Ratio, number, ratio. All right, logos. I would think logos would have been numbers, but hey, arithmos would make sense. Right? Yeah. Okay. Assume for right now, logos, ratio, arithmos, numbers. All right. I have to learn Greek, apparently. Shame on me. All right. I'm educated. I studied Latin in college, one is derived from the other, but not well enough apparently. New transcendental functions. Funks. They're punks, they're funks. Of the two, there is this I had mentioned before, this exponential. And then there's this type. We spent a lot of time on exponential, but because they are inverses of one another, I need to sort of mention them again. These are inverses. Okay. If this is function notation, f of x equals b to the x. Keep picking up the wrong blue. And this is a more self-explanatory way to write it, which is that it's y simply equals b to the x. And these are inverses. Then when you see a logarithm, it would be like this. The x would be down here, and the b would be still in the same place, but your y value would be here. When the input and the output variable are switched, all right, you have a logarithmic expression, a logarithmic function, I should say. All right. It's just that they don't really write it this way so much. You're more inclined to see the reinterpretation of that, which is arranging this in the way that is a little bit more normal in the context that it's y not as the input, even though that's what it really is. Right? It's writing it like this more commonly. Using the word log. So you'll see log, a little subscript b, a parentheses, and then inside the parentheses you'll see x, and then the y will be over here. All right? One of the things that you do for homework is basically translate from logarithmic form to exponential form. These mean the same thing, they're equivalent, but this is writing it so that y is isolated. Okay? And as far as verbalizing that, you would read it as log base b of x is y. Right? The base is the thing in subscripts. All right. Is equals. Of is referring to something in parentheses. The log of x. All right. Base b. Okay. And you could put this in function notation as well. All right. If they wrote it like this, it means the same thing. Function of x. I personally prefer to have things as simply as y and just accept that functions are a strict criteria, right? No repeat x values. Right. Okay, now let's discuss actually converting from the exponential style, which is what this is. This is an exponential form of a logarithm, to logarithmic form. So take out that marker. Leave that there for reference. I have to convince myself not to use certain markers that I have because they don't show up or they're very faint. That one definitely did. Okay, that's going on its way out. That one's good. I like that one. And this particular black is getting faint. Keep it here. All right. Converting. From log form, logarithmic form, to exponential form. Okay. Here's the instruction that I basically write for myself. Right. You read counterclockwise. And you draw a sort of jelly bean. You'll see what I mean in a minute. Draw a jelly bean. So, if you have something that looks like this to begin with, log 3, and if they're a good sport, they would put the parentheses to emphasize that this is the input in this orientation. 2, right? You're going to read counterclockwise like this. I'm really forcing it right now, but you get the idea. Counterclockwise. That is a weird symbol that does not look like a K. And persistent. Something like that. Read counterclockwise, which is reading from here that way. All right, and draw a jelly bean. All right, here's how I mean a jelly bean. Just in time for Easter. All right, that looks sort of like a jelly bean, right? Mmm, flavorful. All right, this thing that was a base, B, is always going to be a base no matter what style you write this. So you're going to have a big 3, but that's its exponent. And that's why you read counterclockwise. 2, and then it's set equal to the thing in the parentheses. That's where you land, 9. And that makes perfect sense, right? Because 3 squared is 9. Okay. Here's another one I'll put over here. Oh, incidentally, the thing that is in parentheses, the thing that is sitting in here, this is called the argument. So if you ever hear that in context, just realize they mean the thing that is the input, really. Of x, the x is the argument. And if you had this, log, little base 6, and then a square root of 6 in here, and then you have 1/2 adjacent. Right. This is in logarithmic form as you see it, but we're going to convert it to exponential form. That doesn't mean that we're making the inverse, it means that we're making it more obvious that it's an inverse. That it is what it is. You read counterclockwise. So draw this jelly bean, right? All right, base is always the base. This is now the exponent, 1/2 equals whatever's sitting in the argument, the square root of 6. And that makes perfect sense, right? Because this just coincidentally is rational notation. Right? Notice the 1 and the 2 index of 2, and that would be here and here if you wrote it in a radical notation. You don't have to worry about that really, but that's from earlier in the semester. Okay. Whatever the denominator is, it's the type of radical. In the case of square roots, they never put the 2, but it could be there. That's where it would be. Okay. All right. Let's say you're going the other way. Like my jelly beans. Red, such a good color. It doesn't go away. Let's see. If you are converting from exponential form, starts out that way, to logarithmic form. Log. Okay. I don't know if only wasn't such a crappy marker. Okay. Let's put that back. Not ready to throw it out yet, but it's getting there. Okay. Convince yourself again. What is the base is always the base. I know that sounds silly, but you know it helps when you read it in context. All right. Basically, make it the bottom of the word log. Right? There's that context of a ratio again. It's a number sitting on top of another number. All right, just not with a fraction bar. Okay. To add to this, see the opposite side of the equals is the argument. It's the thing that gets written in the parentheses of the function. Thing in parentheses is the argument. Okay, here's an example. If you had something in exponential form like 2 to the 3rd is equal to 8, that's true. All right, but remember what this is. This is a big old base. All right. Okay. But you're just going to translate this into logarithmic form as a log. You're going to see the word log. All right. Where does the base go? Down here. All right. Where does the exponent go? On the opposite side. Here. What is the opposite side of equals here? That's the argument. Okay. That's why I like to put the parentheses. Because it helps distinguish the thing that sits here from the thing that sits here. All right. The opposite side of the equals here is the number 8. That goes in the argument there. Okay. Here's another one really quick. If you had 5 to the 3rd is equal to what it is, 125. Taking that and translating it to log, you're going to write the word log. All right. What is the base? The base is always the base. The base here is 5. You're just going to make it down here. Right? Then you have this void in parentheses and the opposite side of the equals. The opposite side of equals here is 125. That goes inside the parentheses. It's the argument. And then the exponent goes here, so it's coincidentally 3. These are the exponents. Okay. Okay, now there's evaluating. This is going to go forever. Okay. Sorry, my camera's getting a little funny here. I'll be right back. sorry. I'll take a little coffee break. Get dry. Let's see. Yeah, I gotta clean that. Let me just spritz this a little bit. Math ant over here. You can't see him, he's out of frame. Hello, math ant. Hello. I'd like to learn some math too. Stick around, chum. I don't think he likes the smell of the cleaning agent. Well, that makes two of us. But I gotta use it, buddy. I gotta get this clean. Alright. Back to work. Alright. Let's see. This is drifting a little bit out of the frame here from pressing on it. This should be tilted back a wee bit. There we go. Yeah. Alright. I have a feeling it's going to drift again, but I apologize. Let's see. Where was I? Okay. Evaluating. Let's discuss evaluating. Logarithms. Okay. The gist of this is to convert to exponential form. And I would say that if you're given no equal sign or ladder and ladder, make one. Make it so. Put the card. I like to use y's a lot of times because that's really what it originates from anyhow. You'll see what I mean. If you start out with something that looks like this, the log, this is not very dry. Sorry. If you have this is terrible looking G. If you have log of 64 base 4 like this, reinterpret the problem. Make it look like this. The log base 4 of 64 equals some letter. It doesn't have to be anything in particular, but I like y. So I'm going to do that. I kind of like to reserve x for this if I could help it, and y for that, but it doesn't have to be. This is y is what they normally would be since it's an inverse of exponential function to begin with. Right. Then we're going to convert it. Right. What does that mean? Convert to exponential form. Draw the jelly bean, right, like that. These two things are y. The base is always a base, and that is now your exponent, right? And you read counterclockwise, right? So if it's the argument is 64, then you have 4 to the y equals 64. And because the numbers are basically integers, right? If it's an integer, then you could infer what the y is. All right, consider for a moment, what would this have to be as an exponent to produce that? It just so happens that 4 times 4 times 4, 3 iterations of 4, all right? An exponent of 3 makes 64. Okay. Let's do another. Maybe I should keep the solution. I don't know what damp cloth. It kind of cleans it a little bit better than my eraser at this point. problem with the eraser is that it kind of spreads residue around and it makes the board a little bit darker. It would be ideal. Okay. Here's another example. If you had the log base 3 of 1/27. Right. I know that it doesn't have equals in the letter, but I would design it, rewrite it exactly like that. Log 3 base 3 of 1/27 is equal to y. Alright, and at this point, draw the jelly bean. So this is really 3 to the y. Whatever variable you want, you read counterclockwise is equal to 1/27. And at this point, again, you could infer what that y actually is. First of all, if you have something that is a fraction on the opposite side, what is the sign of this variable? What would it have to be, a positive or a negative? Well, negatives are what produce fractions. Right? Then as far as the number is concerned, because even if we got this far, even if we got it to be 3 to something negative, we still have to figure out what the number would be in order to produce 27. All right? It would be, just coincidentally, 3 iterations of base 3, 3 times 3 times 3, 3 clones, if you will. So, I shouldn't say, once you move it, it's no longer negative. It would be 3 to the positive 3 after having moved it down here. Up here, it would be negative 3. So then you could say y is equal to negative 3 in this case. Okay. Now a little review of special types of logs. There are 2 special types of logs. Okay. There's what is referred to as the common log. And then there's the natural log. What does that mean? Well, if logarithms have a base, the common log is base 10. Natural logs are base e. Z is a naturally occurring number, believe it or not. 2.71, whatever it is, into infinity. Okay. Let's see. Now, how would you write that? Well, this little dichotomy again. If you were to see a logarithm completely spelled out, which to me would always be the ideal situation for something to be over-explained than to be under-explained, just bear in mind that math people, for the sake of efficiency or whatever is a convenience for them, tend not to write things that they assume. I don't think that's good teaching personally, but instead of seeing this, y equals log with a subscript 10, what you're more inclined to see is what it really, the equivalent, which is simply this. In other words, if you see just the word log, no obvious base, and then the argument, whatever it is, assume that this is what the situation is. It's a base 10, and it would be referred to as a common log. Okay. Similarly, right, rather than have something written like this, which I think is ideal, right, log with an obvious base e subscript, and then the argument here, all right, they have to distinguish it from just simply writing log, right? when the base is e. So what they do, they've come up with a different abbreviation. Right? They, who's they? Script L and an N, right? Natural log, it's just the initial sort of reverse, which I don't know for a fact, but I feel that it has a French origin to it. Like Standard International System of Units, right, SI units. If we say the International Standard, right, rather than the Standard International. Anyhow, if you just simply saw ln and then the argument, whatever it is, x after it, assume that it's really this with the word log spelled out, and that the base should be e. It's more concise to write it like that. Now, just as a side note, if you saw, these are logarithms, right? If you happen to see them in their exponential form, this particular one here would look like so. It would be x is equal to the 10 with a y. And in this case, if you happen to see it, which you probably won't too often, you would see this. X is equal to e to the y. These are equivalent. Right? These are equivalent. Right? It's just, this is the logarithmic style of writing, this is the exponential style of writing. They're inverses of the regular situation, where x is usually the input. Okay. Some water here. Now let's put using a calculator. Let me show you something. All right. If you need to use a calculator, and for this type of thing you would, I think, just to be practical, there's a couple of different buttons. Let me point those out. If you wanted to, this is for TI 83 or 84. Right? If you wanted to use base E, there's this button on your calculator, LN. Right? Which again, remember, it just means this, log base E. Whatever the argument is. And if you wanted to use base 10, used a lot of formulas. All right. This button that is just written as log assumes that that's what you want. To press log means this, right? You just won't see it written. To press ln means this. You just won't see it written as such. Okay. Now, what if you want something else? There's an old-fashioned way of going about it. All right. The situation for any base logarithm. There's two things. That depends on whether your software is updated or not. I would assume that if you got a calculator relatively recently, the software is up to date, and then you don't have to compensate. But here is the key sequence. All right. If you press the MAT button and then scroll down the list, what you'll see as an option is something written like this, a log function. And what it means is that it's a log of a more specific base other than 10, other than E. These buttons are preset to that. And what will show up on your screen, what you'll see is basically this, the word log, an intuitive little box here, and an intuitive box here. You just have to move around with the arrows, decide whatever the base is that you want, decide whatever the argument is that you want. Okay. There's another path that you can get to the same thing. If you have a calculator like mine, which is a TI-84, there's this green button, all right, alpha. And normally that's to choose one of these green letters if you wanted this name of a matrix or something like that. But if you press alpha, it engages one of the function keys that are up here. Behind y equals there's function 1. Behind window there's function 2, and so forth. Well, it just so happens that if you go through this key sequence, alpha, and then I want to say it's window. Yeah. Right. Alpha window engages F2, and a little menu pops up. All right. And I want to say it's the 5th choice in the list. Choice number 5 is log base. Incidentally, if you wanted to convert from a decimal to a fraction, I want to say if you hit the same thing, alpha, but then y equals F1. Yeah, I'll show you. You get more menu options, so let me clear this. Alpha, F2, this menu pops up and there's log base there. All right, quit. If you hit alpha and F1, you have something that goes directly to converting or writing something in the style of a fraction, or converting between a fraction and a decimal. All right, or if you want an improper fraction or a mixed number. All right, these are things that would normally be under the math button. All right, you may have to scroll over to num to get to the same thing. This is a sort of a shortcut that gets you to those features. It's kind of neat. All right, then there are other things here. Anyhow, for right now, alpha F2, if the software is up to date, will get you there. Log base, any type of base logarithm. Or if the software is not up to date, log the bottom of this list, or close to the bottom, you have that choice. And then as if you have an old calculator, like maybe a TI-89 or something like that, pardon me, a TI-80, you know. There's a trick that we used to use, right? Which is called the change of base formula. This is something that I give as part of a handout later. Change of base formula. It's a way of interpreting or getting an equivalent using the log button, the base 10, or using natural log button, base E, to give you the equivalent of whatever you need. So for example, let's say that you had the log of base B and the argument was A. I'm not too clever here. If you physically type this on your calculator, just go for log base 10 of A and log base 10 of B, right? That is, you put the base in the argument. The argument that was there is the top, but if you took the base and you made it the argument of this bottom logarithm, all right, it'll give you the equivalent of this. It's just going to be base 10s if you press the log button, or if you use natural log, it would also work. It's called the change of base formula. It's a way of circumventing an issue if you don't have these functions in your calculator. Alright. There's my family howling again. Okay. Alright. Oh, okay. Let me give you this handout now. This is something that we're going to use over the course of the next week or so. Actually, next week is Easter Sunday, so we have off. Right. Not to bother you with that, I'll mention it again later, but we would have off next week, so the week after. There's this handout, right, which is a summary of different properties of logarithms. The ones that are relevant for today are basically from 1 to 5, right? What I put in red here are basically the effects of what are in purple. All right. Anyhow, if you can, try to print this out. this stuff from here to here, that's section 3.2. And it's useful when you're trying to solve an equation that it involves a logarithm, or if you're trying to simplify an expression. So let's see. Where's this? That was my red again. Not to be gross. I'm not spreading any diseases on my board here, hopefully. That's why it keeps drifting. Yeah, sorry. I keep pressing too much. Alright. Let me go through these. If you're using properties of logarithms, and while we go through this, have this handout close by. Alright, some of these things are self-explanatory. This is using properties of logarithms. And this is essentially for the purpose of simplifying. Okay. As before, if there's no equals and then a letter, throw a letter in there. Use X, use Y. All right, it helps you. Perhaps I'll just point at this for a moment to kind of get through the first couple of them. If you converted, right, I'm just going to kind of scoot this down here to obscure stuff. If you converted log base b of 1 from logarithmic form to exponential form, you would draw a jelly bean around 0 and b, right? And you probably remember from rules of exponents that when you have 0 as an exponent, all right, for almost any base other than 0 itself, this is the outcome, that it equals 1. All right, so to draw a jelly bean around b and 0 and make that base exponent of 0 equals 1 is kind of, redundant. All right, it's self-explanatory. It is what it is. If you have a situation like this, which is why there's no name for these two, b drawn around a jelly bean around b and 1, b to the first equals itself, right? These are the inverses. They're a little bit more complicated, but convince yourself of this. When you have an argument of base b and you have a base b in general, if these are the same, whatever the exponent is here, you could say that that is the outcome. You could expect that to be the outcome. If you have a base that itself has a logarithm as an exponent, it's more or less the same situation. If these two numbers here, they're both bases, all right, are the same number, all right, the argument in the logarithm is the outcome as well. And then we're going to get into the one-to-one property, which we had done before. Okay, so suppose you had this log of 4 to the argument of 1, right? Again, if there is no equals and then a letter, throw in a letter. I'm going to go with X right now. Right? Here's the only thing that I've done to change this situation to my advantage. I'm going to throw equals X here. Normally I would put a Y, but just to get me through this. Right? Draw the jelly bean. Right? What was a base is still a base. 4 to the X. You read counterclockwise, equals 1, right? You can infer what the X value has to be from rules of exponents from way back, right? What causes anything to be 1, well, almost anything to be 1, right? What would the x have to be? The x would have to be 0 according to the rules of exponents. 0th rule of exponents from way back. 4 to the 0 is 1, right? And that is reiterated here on properties of logarithms. Basically, it's this situation. Let's see. B to the 0 is equal to 1. Okay, there's no name for that except that it correlates back to the 0th property, or 0th rule of exponents. Okay. Let's see, here's another. I wish red would erase. Because I like writing in red. It stands out more than the other colors. Okay. Let's see. That's hard, I feel like. Oh, incidentally, for that last problem, if you're comparing notes with the answers in the back of the book, after you figure out what x is, they might have you write it like this. I'm going to put it in a different color. They'll say, what does it equal? It equals 0. All right, that's really what you have to. This is x. Okay. Here's another problem. Suppose you had let's see, the log base square root of 7 of the argument square root of 7. Okay. If it's missing something, missing equals, and then a variable, throw in some other letter. Doesn't matter, it doesn't have to be x. And then draw the jelly bean. Okay. And then you really have this. You could look at your properties and say to yourself, well, when the base and the argument are the same, then the value here should be 1, right? We point at this. When the base and the argument are the same, this is the outcome. But this is proof of that, right? You could infer, as an afterthought, well, what would cause this thing to be unchanged? The x value would have to be 1. Right? And then, as you might see it written in solutions, they would say, well, what does it equal? It equals 1. That's what you really have to. That's the inverse property, and I really messed up my book. My hands are getting really bad. Here's another one. Let's see. 6, and then it has an exponent that is a logarithm of the 6th of the argument 20. Okay. This most closely resembles the inverse, the second incarnation of the inverse property. Where you have a base that is raised here to a logarithm itself. And if the base here just happens to match the base here, then the outcome is whatever the argument is. Okay, so I would bet that this is equal to 20. This base and this base is the same, so whatever is here is the outcome. now let's get into the one-to-one property again. Now we discussed one-to-one property for exponential functions, or exponential equations. We're going to discuss the one-to-one property applied to logarithms. I want to again refer back to the original handout, which I was saying it's not really important for today, but it will be in the long run. There is this diagram, which is specifically for solving equations that involve exponential or logarithmic expressions. If you decide that you have an exponential equation, something that has this as the main feature, the key feature, pay attention to the techniques that are on this side of this line. Right? We haven't gone into a lot of them. The only one that I really discussed was this one, when you have the same bases, or if you can convert something that does have the same bases, then you use the one-to-one property. The only reason I'm mentioning it now is because now we're going to be discussing logarithmic equations. That is where that's the key feature. And you notice, once again, there is a one-to-one property for dealing with this. What you'll see is that there'll be a log of some argument set equal to a log of some other argument. And in this case, these would both be base 10s. So if they have the same bases, then you could just set the arguments equal to each other. Anyhow, if you can print that diagram out, we're going to use it a lot when we get to section 3-4. All right, it's a nice overview, I hope. But for right now, we'll just deal with one-to-one. All right, so using one-to-one property for logarithms. Okay. This means that they have the same bases. So you set the argument of the first equal to the argument of the second. Here's an actual example. Let's see. I suppose you had log of base 3 of x. And this was part of an equation. This was part of an equation, so you see equals. And then there is the log, also base 3, but the opposite side of equals is the argument 12. Right. Same bases, you could say that x is 12 in order for them to equal in terms of whatever their decimal is. Okay. If you had something a little bit more interesting, like an algebraic expression that was more complicated than just the letter x. Let's see if you have this. Log of 2x plus 1 equals log of 3x. All right. Although it's not written, these would be base 10s. So you can apply the one-to-one property. The argument of the first set equal to this. So if you have 2x plus 1 equals 3x, you have a simple algebraic equation. You could rearrange at will. I'm going to move the 2x over here. If this is assumed to be positive, to justify moving the whole chunk, the whole term to x, subtract. Whatever you do to one side, do to the opposite side. This positive 1 is left over. There's a cancellation effect, because even if it's mysterious, something minus itself is 0. And then 3 minus 2, they're like terms, you're just left with x. So x is equal to 1. Just written backwards. Okay. If you have something even more complicated than that, say that you ended up with something quadratic or square, you may end up having to factor and use the zero product rule, but no sweat. Let's see what you got. Let's see. Suppose you had a log of 4, x squared minus 6 is equal to the log of 4, and the argument is 10. They are both base 4s, so you're going to basically ignore that. And then simply borrow these two features. X squared minus 6 is equal to 10. And then rearrange it. In theory, you could probably do this two ways. You can move the 6 here, and then you get 16. Right? Or you can move the 10 here and then use the zero product rule. It doesn't really matter. Just bear in mind, normally, if you that would involve taking a square root if you move the 6. Don't forget that there is, in theory, a positive outcome and a negative outcome. I think maybe if you moved it like so, let's see, is that positive? Yeah, you would get a 0 here, and perhaps at this point in the semester you go, all right, negative 16. This is the difference of two squares model. It's a bit disguised to see 16 there, but this is the same as saying x squared minus 4 squared, the difference of two things that are squared, and simultaneously set equal to 0, which means that if I factor it, all right, then I could take advantage of the zero product rule. All right, the way that difference of two squares factors is nearly identical. This should be a 4, sorry. Let's see. Except for their signs, there would be one negative, one positive. Right? And according to the zero product rule, you could write a smaller equation, x minus 4 equals 0 here, and x plus 4 equals 0 here, in which case x would be positive 4 in one instance, and x would be negative 4 in the other. You get two answers, right? That's natural for something that is square to begin with. If you did it the other way, no sin in that. I'll put it here. In which case you moved maybe the 6 by adding. Right, then you would have x squared equals 16. Just remember, when you apply opposite operations, in this case the opposite of squaring is square root, that you put plus or minus in this case. Right? Normally we're more obsessed with the positive answer, but theoretically it is possible to get a negative. Negative 4 times negative 4 still makes positive 16, right? So x is equal to plus or minus 4. Okay. All right. Let's get into graphs. In time, we're at the 3 hours already. Oh, Red, you're not a permanent marker. Why are you acting like that? It must be industrial red. Let me give you some information and then I'll slip in a drawing here. See if I can keep that stuck on one side. That kind of fits. Okay, good. All right. Talking about graphs of logarithms. The key thing to remember is that this is the inverse of exponential function. If exponential functions look like this, I'll put this in red. they run like this. There is, I shouldn't do that, but let's see the green. There is a horizontal asymptote that runs along the x-axis. And a key point for it seems like every type is 0, 1. There's a y-intercept for exponential. Then, as the inverse of the exponential function, the logarithmic function should be the reflection of that, right? The reflection of that over, I don't know if you remember, y equals x, right? Inverses do that, right? They basically switch x and y values. So if the perhaps most interesting point for an exponential function is 0, 1, then what you would see is that it would be 1, 0. Would be a key point for a logarithmic function. It turns out that the logarithmic function is going to run like this. Right? And in theory, I'm going to get a straight ruler here. If I took the time, I'm trying to make this as nice as possible. If I took the time to draw a dashed line exactly at a 45-degree angle technically, which is the y equals x linear diagonal equation, right? They would be the mirror image of one another reflected over this diagonal line. All inverses behave that way. Right? You basically switch the x and y values. Right? Before, we had calculated, and I'll sort of show you here. By hand, brute force, I don't want to do it twice. Let's see. Lazy. Before, we generated these coordinates, right? Brute force, using these inputs for x's, right? If I took these coordinates, right, and switched the x value with the y value, that is, you have 1/8 and then -3 would be here. 1/8 is just ever so slightly moved over along the x-axis. All right, and -3 would be 1, 2, 3. You have a point that makes up this curve that is in blue. All right. Again, if I switched the next one, I'll do one that's a little bit easier. -1 and then half. If I switched it as being 1/2 and then -1, 1/2 is halfway here, right? And then 1 would be here, right? And then there's the obvious, nice, satisfying whole number, 1, 0. And then continuing, switch 1 and 2, make it 2, 1. Over 2, up 1. Switch 2 and 4, make it 4, 2. 1, 2, 3, 4, up 2. You see that you have this curve instead. Right? That's how logarithms behave. Now, if exponential functions have a horizontal asymptote and a logarithmic function is its inverse, And log functions have a vertical asymptote. And you could see from the calculations that that is the truth. All right, so to summarize, let me put that here. Exponential function. What does it have? Key features. It has a y-intercept at 0, 1. And it has a horizontal asymptote, y equals 0, better known as the x-axis. At the same time, log function has an x-intercept at 1, 0, and it has a vertical asymptote. Right, at x equals 0, better known as the y-axis. That's kind of a funny way to spell this. Alright. Then there's transformations naturally as well. Let me just show you how it's adapted. Again, this is the old model. The function is equal to plus or minus some compression or, pardon me, vertical stretch or compression factor, dx minus h plus k. How it's going to be adapted would look like this. Plus or minus a log, and then the argument. Let's see. X plus c plus d. Okay. These correlate. If you're wondering about the b, all right, it's not something that you have to worry about, right? As in the case of our exponential, the b was used in the context of base. Right? And logarithms, in theory, have a base. Right? More importantly, right, beware of these because they're counterintuitive. Right, this is the horizontal shift again. These are the vertical stretch, compression factor. These cause reflection, vertical reflection. And these are the vertical shift. It's the horizontal shift that's always the nuisance. Let's do one. Right. If again, this is how a logarithmic function would look to begin with. Something like that. Let's see what it would transform into if you had this. Y equals log of x minus 1. Okay. Compare the thing that you're given to the adapted model, right? The only feature in this example that seems to be additional, right, if as opposed to just this in blue here, this would be y equals the log of x. The only feature that you see added is that nuisance feature, the horizontal shift, which again is counterintuitive. So if you see a -1 here, it means the whole picture is going to be moved left or right, but it's going to be towards the right, ironically. Shift +1 to the right, that way. So take that key point, all right, and add 1 to it, which means that you would have a point like this, right? That would cause, naturally, the asymptote to move forward as well. And then your picture would look something like this. Okay. If you want, I mean, I would try to do something by hand just for the experience, but use your calculator to experiment. Turn it on. Turn it on. It's that button, Ziggy. Okay. Okay, you can clear out this stuff. And I'll clear out that as well. Put in the original one on top, right? So it's log base 10 apparently. So you have a log button here. Log x. And you could be a good sport and close the thing. Then hit graph. And you see there's the picture. It's kind of far away, so if you want, go for fit. Zoom fit. Might give you something a little bit more satisfying. It's a little bit closer. That looks nice. All right. Again, if you hit trace, it'll tell you at 0x that y is undefined. There's no value here because it's undefined. That's the asymptote, the vertical asymptote for a log. If you wanted to enter, once you hit trace, you can enter values for x's. Press 1, it'll spit out what the location is at the intercept here. Right. Now I'm going to superimpose the transformed incarnation of this log and experiment with just putting, I'm going to put minus and then 1. Incidentally, be careful, right? Unless you're using a negative as a coefficient, avoid this button. Don't use these interchangeably on a TI calculator. For whatever reason, it just doesn't understand that they're the same thing. All right, there's the function that we have. And now hit graph. And you see it just scoots it over, right? If you want to read this one with trace, you'll have to shift potentially. There's a cursor, which is probably off the screen here. Notice that what shows up in the corner here is the actual function that it's tracing. Up and down arrows seem to control shifting from one to the other. Anyhow, you see this high degree of precision, but even if you scooted this over to where you expect it to be 1 and 0, or in this case 2 and 0, it's never going to be right on it. It's a little annoying. So make an educated guess. It should be 2 anyhow, and you could validate. That's a 5. 2, and you'll see that it's 0 right where it's supposed to be. Because all we did was horizontally shift. Okay. Let's see. I'm going to use properties of logs again. We'll use properties of logarithms now with the base e. natural log. They correlate, and we're just going to simplify for right now. So if you had the natural log, which would be abbreviated as ln, and then you had this as the argument, 1 over e. Right? What I would do is, first of all, complete the parentheses, translate into the over-explained logarithmic way of writing. You know, full, for lack of a better expression, log notation. See what I mean? You took this and you use the actual word log. If it's a natural log, it's a base e. The argument that is here is still the argument that would be here. Okay. Now, what we could do is take advantage of rules from exponents from a long time ago. Again, this is something that is written in the style of a fraction. So if you wanted to reinterpret that, right, remember that if we moved the orientation of this from a denominator to a numerator, it would basically restore it to having a negative exponent. Since there is no number written here as the exponent of e, assume that it is a 1. And now that is the argument. And that means that this is log base e of the argument e to the 1. I'm going to refer again back to properties of logarithms page. Okay, and see what this most closely resembles. You have the situation where the base here and the base of the argument are basically, that's a bad choice of words, but essentially are the same. So therefore, whatever the exponent is, that's the outcome. This, therefore, equals -1. I prefer, personally, to just simply write it like that. But you might see it written as equals -1. Now, it is the inverse property. Okay. What if you had something like this? Full-fledged. Suppose you had 2 times the natural log of e. Not too creative here. Again, if it helps, convert this to full-fledged log notation, which means that this would be the log of base e to the argument e, with a 2 next to it. And again, referring back to that paper, what does this most closely resemble? This chunk of it, from here to here at least, log e of e, base e. It is this, right? When the bases are the same, they just happen to be e's, the outcome is 1. Which means that this is really 1 times the 2 that is there, which means that this is just equal to 2. Okay. One more thing and then I'll stop. If they ask you about the domain of a graph, you have a reference already, but you might want to draw the picture either by hand or using a graphing utility, your calculator in theory. Let's do this. If they ask you to find the domain. Okay. And here's the function. Function in function notation of the natural log of x minus 2. All right. What does this translate to? Well, if instead of using function notation you went with y, and instead of using natural log you went with log base e, this is what you would have alternatively. What I would suggest you do, however you do it, by hand or with a calculator, and a calculator might make it faster, is draw, graph what you have. And then compare to the normal situation. Now, I want to refer to one of my handouts here. Again, available for printing is this. This sheet again. Here's section 3.2. A natural logarithm is a logarithm that still goes through that point 1, comma 0. So it still makes this curve, just might be a little bit sharper this way. And it still has a vertical asymptote like this. Notice what it says. The domain is not including 0, right, because the boundary, that is the asymptote, is x equals 0, so we don't include that, but it's a reference, right? And it could be anything into infinity in terms of x's. The range, on the other hand, could be anything from negative to positive infinity, all real numbers, right? What's going to change is the domain is going to change, right? And if this is the interval notation, 0 comma negative, pardon me, 0 comma infinity, if you change the position of this from being one comma 0, from here to, bear in mind, this is counterintuitive, and it's the C doing the job of C or H, whichever you like, of a horizontal shift. Move this point, right, towards the right. So in other words, if you take 1 and you added 2, because it's negative here, right? Right? Scoot over. This is 1, then you're going to add 2 to that. 1 plus 1 is 2. 2 plus the additional 1 is 3. Right? You now have a curve like this. Right? And note how that affects the asymptotes. If the asymptotes, vertical asymptote, is x equals 0, if you add 2 to that, right, then it is right on 2. This point here would be 3 comma 0, but the asymptote would be x equals positive 2. Okay, that affects the interval, and that interval affects the domain. So what is your domain going to be? Right, under the normal circumstances, right, what is in red? Domain, this is normal situation, right, in interval notation, it is normally this. It does not include 0, which is why this is a parentheses rather than a bracket. This is dying. This red. And it goes into infinity. You can have x not including 0, just merely as a reference, and anything into infinity that way. Right. If, in consideration of the black line, the domain for the transformation would be, instead of 0, where's the asymptote now? 2, but still arcing into positive infinity. Okay. So right here. me leave it at that. All right, I'm at the 3 hour, 45-minute mark. Let me show you the calendar, because we're on track, basically. Here's our regular calendar. We're only on Sundays, of course. All right, here's where we are today. We covered section 3.1 and 3.2. Next week we have off for Easter, so there'll be no video. Just work on these problems. And then the week after that, we're going to do 3.3 and 3.4. All right, and then the week after that is the last stuff, section 3.5 and 2.5 and appendix A5. All right, and that's it. As far as the final exam is concerned, they still haven't said what we're going to do about that. Worst case scenario, I'll make it a final exam and just let you have it. All right, so you can see a nice summary of stuff, but that's about it. All right. Otherwise, I don't know how I could possibly collect it from you. All right. Anyhow, thanks for spending the time with me today. All right. Stay safe, folks. Just try those textbook sections 3.1 and 3.2. See you next, not next week, but the week after. Okay, so what day is that? I'll talk to you again on April 19th. All right, if not sooner via email. All right. Okay, take care.